Imagine arriving at work. You park your car, put on your equipment, meet the people on your shift, and then, instead of walking into a building, you begin traveling downward. Not one floor, not 10 floors, not even 100. You keep descending until the surface is no longer a place nearby. It is kilometers above your head. At Mponeng Gold Mine in South Africa, mining takes place between roughly 3,160 and 3,140 meters below the surface, more than 3 kilometers underground. Harmony Gold describes Mponeng as the deepest mine in the world. At that depth, something strange happens to the idea of going to work. You are not simply entering a workplace, you are entering the earth, and somewhere down there, people still have to do completely ordinary human things. Breathe, drink water, move around, communicate, stay cool enough to work, know where they are, know how to get out, and eventually return to the surface, which creates a surprisingly complicated question. How do you build a workplace for humans more than 2 miles underground? Because the obvious answer is, dig a hole. And technically, that is an excellent beginning, but it is an absolutely terrible complete plan. A hole does not give you breathable air. A hole does not remove heat. A hole does not transport hundreds or thousands of people and machines. A hole does not tell you what the rock around you is doing, and a hole definitely does not provide an emergency exit simply because everyone has decided they would very much like one. A deep mine is not just empty space underground, it is infrastructure, and the deeper you go, the more infrastructure matters. Start with the first problem, getting down there. Mponeng's infrastructure includes a main shaft supported by a subshaft, because at these depths, the vertical journey itself becomes a major part of the mine. A shaft is essentially one of the mine's connections between 2 completely different worlds. At the top, sunlight, roads, buildings, fresh air. At the bottom, rock, artificial light, tunnels, machinery, and more rock. A truly unreasonable amount of rock. Mining regulations treat underground transportation as its own major safety problem. South Africa has dedicated guidance covering underground rail-bound equipment, trackless mobile machinery, and other systems used to move people and material through mines. Because reaching the working area does not necessarily end when you reach the bottom of a shaft. A deep mine is not one giant underground room. It can contain levels, tunnels, haulages, and working areas extending through a large 3-dimensional network. So the journey becomes layered. Surface, shaft, underground level, transport, working area. Your commute has developed a geology problem, and this creates the first major difference between deep mining and almost every environment we have explored so far. On a submarine, the entire habitat moves with you. On an offshore platform, you live where you work. In Antarctica, the station becomes your home. But in a deep mine, the goal is not to live underground. The goal is to go incredibly deep, work there safely, and come back. Every shift. Which means the mine has to repeatedly move human beings between the normal world and an environment that only exists because engineers continuously make it usable. And perhaps the most obvious example is air. You may be kilometers underground, but your lungs remain stubbornly committed to surface conditions. They have not received the memo, so air has to move through the mine. Ventilation is one of the fundamental safety systems of underground mining. NIOSH describes proper control and distribution of ventilation air as crucial to worker health and safety, while atmospheric monitoring can be used to track airflow and detect dangerous gases or combustion products. Think about what this means. At the surface, opening a door gives you atmosphere. Underground, air becomes infrastructure. It has direction. It has routes. It has quantities. It has measurements. It has engineering. Large ventilation systems move fresh air toward areas where people work and help move contaminated air away. And auxiliary ventilation can be needed to get airflow into particular headings and development areas. The mine is effectively building an invisible river, except instead of water, it moves the thing everybody is breathing, which is slightly important. And air underground has enemies: dust, equipment emissions, heat, potential gases, smoke during a fire. All of these turn something humans normally receive for free into a managed technical system. NIOSH has emphasized ventilation as an integral part of modern underground mining, both for air quality and for controlling worker exposure to hazards generated by mining activity and equipment. So already, before anybody actually removes rock, the mine has to solve one of the same problems as a submarine. How do we keep the atmosphere around people usable? But then depth creates another problem: heat. This is one of the least intuitive things about extremely deep mines. You descend away from the sun, and somehow heat becomes a greater concern. NIOSH notes that heat risk grows as underground mines extend into deeper, hotter areas, and occupational heat stress can lead to heat exhaustion, heat stroke, and other illnesses or injuries. The surrounding rock is not sitting at comfortable office temperature waiting for humans to arrive. At great depth, the underground thermal environment itself becomes something that has to be monitored and controlled. South Africa's mining regulator requires monitoring of worker exposure to thermal stress, and specifically classifies underground heat conditions using measurements including wet bulb and dry bulb temperature, which means temperature. Underground is not simply, wow, it feels warm. It becomes data, because a miner performing physical work generates heat. Protective equipment can make heat harder to lose. Low air movement makes cooling harder. Humidity matters, and the environment may already be hot. The human body has now become one more machine with operating limits. Except unlike most machines, when this one overheats, giving it a firm slap does not improve the situation. Heat management therefore includes things that sound extremely ordinary: water, rest, acclimatization, monitoring. NIOSH specifically recommends hydration, appropriate rest periods, and adjusting work rest schedules as heat stress rises. South African mining guidance also requires potable water to be available to employees during very hot conditions. And that gives us another recurring, oddly possible pattern. Take a human away from civilization, and suddenly boring things become engineering: a glass of water, a breathable room, a comfortable temperature. You do not appreciate them until they become difficult. But heat is not the only thing created by going deeper. There is also pressure, not atmospheric pressure like a diver experiences. Rock pressure. Above you are kilometers of earth. And rock under enormous stress does not always behave like the decorative stone on somebody's kitchen counter. Mining changes the stress around excavations, and sometimes the rock responds. South Africa's Mine Health and Safety Inspectorate identifies falls of ground as a major underground mining hazard and notes that rock bursts become particularly significant in deep gold mines, with risk increasing at depths beyond 3,000 meters. This changes how you think about a tunnel. To us, a tunnel looks like empty space carved through solid rock. To a mining engineer, it is empty space carved into a material carrying enormous forces. The rock is not scenery, it is part of the system, and sometimes part of the threat, which means another hidden system becomes essential: ground control. The mine has to understand the rock, support it, monitor it, design openings around it, and constantly respect one uncomfortable fact: the mountain was perfectly happy before humans arrived. We are the ones insisting on putting hallways inside it. This is why deep mines feel fundamentally different from caves. A cave is a natural space humans enter. A deep working mine is an engineered environment humans continuously maintain. Ventilation must work. Transportation must work. Ground support must work. Communication must work. Water must be available. People must remain physically capable of working. And then there is the question nobody wants to need. What happens when something goes wrong? Consider where you are. Maybe 3 kilometers underground, there is smoke, or a fire, or damaged infrastructure, or a rock fall. On the surface, an emergency exit is usually designed around one extremely useful concept: outside. Walk through a door, and the building is behind you. A deep mine does not offer this luxury. Outside may be kilometers away, vertically, through underground workings, then through transportation systems, then through a shaft. So escape itself has to become a system. South African mine safety rules include dedicated guidance on emergency preparedness, fires, self-contained self-rescuers, and the right of workers to leave dangerous working places. One particularly interesting piece of equipment is the self-contained self-rescuer. An SCSR is a portable breathing device, providing its own oxygen supply when activated, giving miners breathable air in situations such as underground fires or explosions while they attempt to escape a hazardous area. Think about the psychology of carrying something like that. Most workers bring equipment because it helps them do their job. Some underground equipment exists because one day, the normal atmosphere may stop being safe. And if that happens, you cannot simply hold your breath until you reach the parking lot. The parking lot is 3 kilometers up, which is inconvenient. Emergency planning therefore has to assume something uncomfortable. The systems you normally use to leave may themselves be affected by the emergency. That is why underground mining treats escape, rescue, and emergency response as separate technical problems rather than just pointing toward an exit sign. Other mining jurisdictions use similar layered approaches. In the United States, for example, MSHA requires underground coal mines to account for communications, tracking, emergency escape, and refuge alternatives, with escape treated as the first line of defense. The exact rules and equipment differ between countries and mine types, but the underlying problem is universal. The farther underground you put a human, the more seriously you have to answer the question, how does that human come back? And communication becomes especially interesting. On the surface, losing contact with a coworker is annoying. Underground, location and communication may matter during an emergency. Mining regulators and researchers have therefore spent years developing and evaluating underground communications and personnel tracking technologies because ordinary communication methods can be limited by the underground environment. Again, the mine is recreating something the surface gives us almost invisibly: connection. And by this point, something should be becoming clear. A deep mine is not one engineering problem. It is a chain. Air allows people to enter. Heat control allows them to remain functional. Transport gets them to the working area. Ground control keeps that area usable. Communication connects them. Emergency systems give them options if normal operations fail. And all of these systems depend on people inspecting, maintaining, and operating other systems, which means the deeper mine is beginning to resemble something familiar. A tiny underground civilization, not because anybody wants to live there, that would be a questionable housing decision, but because humans bring civilization's requirements with them, even when they only intend to stay for a shift. And if you enjoy seeing how humans make ordinary life function in places where ordinary life should be impossible, subscribe, because that is exactly what this channel explores. Now consider the strangest part of the mine: time. Imagine beginning your shift in daylight. You descend. The sun disappears. Eventually, natural light has absolutely nothing to do with your environment. There is no sunrise 3 kilometers underground. No clouds, no evening, no horizon. There's only artificial light, the work, and the schedule. Then, hours later, you begin moving back toward the shaft. You travel upward, and eventually, the world returns. Sky, wind, temperature, weather, a horizon, maybe daylight, maybe darkness, depending on when your shift ends. It is almost the reverse of the submarine problem. A submarine takes a tiny surface world and carries it underwater for months. A deep mine repeatedly takes humans out of the surface world, moves them into a manufactured underground one, then brings them back. And this has an EI. Important consequence. The deeper the mine becomes, the more expensive every minute underground becomes in human terms. Workers need to reach the workplace, work, and return. The mine cannot simply teleport them to the rock face. Unfortunately, teleportation remains underfunded. So access itself matters. Transportation matters. Equipment reliability matters. Planning matters. Fatigue matters enough that South Africa maintains specific guidance requiring risk-based fatigue management at mines, because an exhausted person operating inside a hazardous environment is not merely uncomfortable. Fatigue changes risk, and underground mining already has enough risk. The rock does not need assistance. There is also health beyond the immediate shift. Mining regulation addresses worker exposure to airborne pollutants, noise and thermal stress, and employees exposed to occupational hazards undergo medical surveillance. This reveals another hidden part of deep mining. You do not merely design the mine around whether a human can survive underground today. You also ask what repeated exposure does over time. Dust matters, noise matters, heat matters, physical strain matters. And this means the human body becomes something the mine must monitor, almost like another critical system. Not because workers are machines, but because they very specifically are not. A pump can be replaced. A ventilation fan can be repaired. A rail system can be maintained. Humans require a much stranger collection of things: air, water, temperature control, rest, health monitoring, training, information, escape, trust, and perhaps most importantly, confidence that all the invisible systems around them are doing what they are supposed to do. Because imagine standing kilometers underground. You cannot personally inspect the entire ventilation network. You cannot personally inspect the entire shaft. You cannot personally calculate every rock stress. You cannot personally monitor every emergency route. You are depending on a civilization of specialists, ventilation people, engineers, geologists, rock mechanics specialists, safety personnel, medical personnel, maintenance teams, transport operators, emergency responders, and the people working beside you. This is why a deep mine may look like one worker drilling rock, but that worker is standing on top of an enormous invisible support network. The drill is obvious. The systems keeping the human capable of holding the drill are less obvious. And that may be the real story of deep mining. The deeper humans go, the less the mine resembles a hole. At the surface, you see a headframe, buildings, shaft infrastructure, maybe equipment. Then you descend, and hidden underneath is another engineered world. Air moves through it, people move through it, machines move through it, electricity moves through it, information moves through it. Rock is supported around it, heat is monitored, hazards are measured, emergency equipment waits, and somewhere inside all of this, a person is having a perfectly normal workday. As normal as a workday can be when the nearest patch of grass is 3 kilometers above your head. Eventually, the shift ends. The equipment is left underground. Workers begin moving back, through the tunnels, toward transport, toward the shaft, then upward. For most of the shift, the surface may as well have been another world. Now, it slowly comes closer, and eventually, a door opens. Natural air, sky, noise from outside, cars, roads, phones, food, home, and almost instantly, all those underground systems disappear from attention, because the surface is extremely good at making human survival look simple. You breathe without asking where the air came from. You walk outside without planning an evacuation route 3 kilometers long. You turn on a tap without calculating heat stress. You travel across town without thinking about shaft infrastructure. You stand under the sky without considering whether the roof needs rock support. Deep mining removes all of that convenience, then rebuilds enough of it, underground for humans to work. That is why the impressive thing about the world's deepest mines is not simply their depth. Yes, more than 3 kilometers underground is absurd. At Mponeng, Current mining depths reach as far as about 3.74 kilometers beneath the surface. But depth is only the beginning of the achievement. The extraordinary part is what has to follow humans down there. Air, transportation, cooling and heat controls, lighting, power, communication, rock, support, water, medical systems, emergency equipment, escape planning, people trained to keep all of it working, because you cannot simply dig deeper and expect humans to follow. Every additional meter creates another demand: more distance, more heat, more rock stress, more infrastructure, more dependency. Until eventually, you realize that a deep mine is doing something much stranger than extracting rock. It is extending the conditions of human civilization downward into a place where those conditions did not exist. The miners are not simply working 2 miles beneath the surface. They are working inside a tiny piece of the surface world that we built underground.